we are recommending to you guys. So then if you are facing, I think I received a couple of messages from some of you today requesting for clarification on some subjects and other concepts that have been introduced to you already. So if you have any issues or problems, don't hesitate to reach out to me personally or through the classroom.
Please,
Yeah,
what's this?
so I was supposed to meet you last week, but then due to some inconveniences and some busy schedules, I wasn't able to meet you, and that's why we've scheduled the session to today. So I'm going to take you through is an introduction to techniques for building predictive models. Then I'll just quickly take you through linear regression, the mathematics behind linear regression. It's actually not magic. It's just mathematics. The whole thing about prediction, the whole thing about modeling has to do with mathematics. So it's not about magic or something that yeah, you can't really fathom. So once I introduce you to the mathematics behind all those algorithms, you get to understand why those things are possible. Then I'll quickly take you to some of the essential things that makes the prediction possible, such as the hypothesis function, the cost function, the gradient descent. And then I'll talk more about a different algorithm known as the logistic regression. Then right after that, I'll talk about the ensemble methods. There are a lot of ensemble methods and bootstrapping, aggregating or bagging, which is the decision tree, the random forest, and other important algorithms that are based on the idea of using decision trees. Then right after that, we go to the practicals where I will introduce you to how to actually build these algorithms from scratch. You build your own algorithms, so it's not like the usual way that you just have to import the library directly from sklearn and then you fit your data set to it. I'll try as much as possible to take you through the basics, the mathematics, and how to code the algorithms from scratch. So uh, the sessions are going to be today and on Friday. So based on how fast we move, we'll see whether we can utilize those 2 days to finish everything. Yeah, but before that, do you guys have any questions or concerns or queries that you'd like to let me know about? Do you have any question, or I can just proceed with the slides?
Yeah,
All
you
right,
can
so
proceed.
I'll be starting now. Yes.
I was saying you can proceed.
So I'll be starting now. If you have any other question, feel free to leave them in the chat box, and I'll make them and read them out and hopefully answer them. So first of all, I'll talk about the linear regression model or the algorithm that we are all used to. I think we've learned them in high some of us. It was introduced to us in high school. Others learned it in college and in our master's program. So, for instance, if you have a lot of data points and these data points have been plotted on a scatter diagram, how can you actually build a model as in a linear function to distinguish between the data points? I mean, the data point that you can actually see um, located here right on my far left. You realize that this is a scatter plot of a particular data point that have been plotted. And the main idea is that how can you model this particular data point? I mean, you coming up with a mathematical model, a linear function to distinguish between this data point. That is the whole idea of linear regression. And if you look at the second image, you realize that, of course, we've been able to come up with a linear function to distinguish between the data points where some of the data points are located on uh, the lower boundaries, and then others are located right on top ahead. I mean, on the upper side of the linear function. So it means that this is the best way this linear function can actually distinguish between the data points that we have. Now, once you have this model or this linear function, how can we come up with devise a method or come up with a methodology to make sure that we tweak our parameters in a way that our linear function can be remodeled or resketched in a way that we can find a feasible way to distinguish between the data points. And that is exactly what the third image, yes, third sketch is doing. So what we do is that we use what we call the loss function, which is simply we look at the differences between the data points in the model and then the ones that have been predicted. We take the difference and we consistently tweak some model parameters to make sure that we get a feasible linear function that accurately distinguish between the data points. And then the idea of accurately distinguishing between the data points means that the model will be able to give us a very good performance, that is accurate performance. So, and that is just a brief motivation behind the linear regression. Now, what really is linear regression? We've been hearing about linear regression. What is it about? So linear regression is simply a model. You can also think of it as a function. When you finally code it and it is functioning, then you refer to us as an algorithm. So it simply assumes the linear relationship between some input variables or input features and then an output variable, which we normally refer to as a target. So what this linear regression model does is that it simply attempts the relationship between these two variables, and it does it in a way by fitting a linear function to the observed data. The observed data simply represent the model that the data points that we want to fit the model. So in actual sense, that is simply what that is the actual explanation to a linear regression model. I'm coming in a minute. Yeah, so so that is what I'm saying, that the whole idea about the linear regression model is to attempt uh, fit to attempt the relationship between these two variables by fitting a linear equation, that is a linear function, to the observed data set. And here the observed data set simply refers to the actual data point or the observation that are used to estimate and fit a regression model or the regression function. So we'll be looking at what observed data points means and then what predicted data points actually mean. So in a typical linear regression model, the input variables are normally called the independent variables, which we learned some of us learned in high schools and in college. Another name we normally give to these input features or input variables is the explanatory variable or features, and it's mostly denoted by x. And the output variable is what you normally refer to as the dependent variable or the response variable. In other literatures, we refer to them as target. I think target is one of the accurate way of calling names given to, I mean, accurate names given to the output variable, and this output variable is mostly denoted as y. Yes. So in a typical supervised learning process, or and that is a subcategory of machine learning, the data set that we normally use to train the model is called the training set, and this training set is mostly denoted by M. So for the first tuple that you see here, that is x1 comma y1. Here you see the x1 simply refer to the input features, which normally comes in the form of a matrix, and then the y1 is the output variable or the target, which normally comes in the form of a vector. And this simply denotes the first training example for the data set. So it means that the last training example will be denoted as x to xm and then ym. So if you have a question, feel free to leave them in the chat box, or you can just raise your hand and I'll call you out to ask the question. Yes, Benjamin, I'm listening.
Yes, sorry, I have questions. Will you kindly repeat those variables x and 1 and y? Sorry.
Could you speak up a bit?
Could you kindly repeat what those variables indicate? The second set also, I think, there's a variable. Yes, there's xm and ym.
Yeah, so xm and ym simply refers to the last training example. It's, these things are samples. So for instance, if you have a collection of data points that are represented in a data frame, the first row can simply be what I am referring to as the x1 y1, where the x1 simply refers to the data points, the input features, which normally comes in the form of a matrix. So if you look at the ARIS data set that we looked at last week, so the x1 simply refer to all the features that you are looking at except the target column. And then the xm and ym is the last row, can be just represented as the last row of the last training example from the data set that we will be having. So the xm, and then the xm comes in the form of a matrix, and then the ym comes in the form of a vector. So I hope this helps. Is that clear, or you need more clarification?
It's quite clear. It's better. Maybe we needed to take notes of how you've explained them in line with the dataset example.
So let me try and then see if I can get a data set to explain what I'm trying to mean by of the input features that I was talking about. So what you see here is simply a multivariate linear regression, which means that here we have several input features. So this comes in the form of a matrix where the values that are going down from left to down simply refer to the Come again? Sorry, I didn't hear you. What did you say? All right, so from where the M data samples simply refer to the rows, okay, that we are looking at. And then if you take each of the columns simply refers to the features, the number of features that you are looking at. Now, this x value normally comes in the form of a matrix, which is what I was trying to explain to you. So it comes in the form of a matrix, which can also be interpreted as row vector of n elements. So the x1 that I was telling you is simply a row. So you take just a row of these input features that we have, and then you use that to fit the model. The corresponding y variable, which is your target variable, also come in a form of a vector. Okay, I hope this visually explains what I was trying to um, explain to you, right, Benjani?
Yes, yes, it
Is
helps.
it clear now?
It helps a lot. Yeah, thank you.
Okay.
Sorry, Prince. Sorry. Just on this, what about the
Yes.
Y? Which one is the Y?
Yes. So the y also comes in the form of a vector. So instead of the matrix that I'm having here, the y simply comes in the form of. Is that clear, Benjamin?
Yes,
Can I
yes, please.
proceed?
Yes, please.
Okay. All right, these are great questions, and I encourage you to ask more questions, more challenging questions, and then other questions to clarify points and if you don't understand anything. Yeah, so thanks very much for that question. All right, so let's proceed. Now, so the whole idea about the linear regression is to look out for what we call the hypothesis function or the objective function. So in linear regression, the hypothesis function normally denoted by h, and is simply a function that maps the input features to an output feature. So you have an input feature or input features that predicts an output feature. So that is the main idea of a hypothesis function. So it's like the hypothesis function is simply some kind of an intersection, a function that connects the input feature to the output feature. So it simply takes in input features and then transform or perform some kind of mathematical computation that predicts an output feature or an output value. So if we simply assume that there's a linear relationship between uh, your input features and then your target, which is your output feature, then it means that the hypothesis function will be represented in the first equation that I have here, that is h theta of x equals h naught plus h1 x. So in this case, your h naught and then the h1 are simply what we normally refer to as model parameters. And these model parameters are parameters that we normally take to make sure that we get a feasible value to maximize the accuracy of the model. The theta naught simply refers to the intercept, and then the theta one is what we normally refer to as the slope or the gradient. And you can see that this function is nothing but nothing but the linear function. Yes, so as I mentioned earlier on, your yi values simply are values that are subset of your bigger y, and your bigger y here simply refer to their labels, and they are labels of the data set. And your x values are simply your input features, and this ranges from 1 all the way to n or all the way to m. And because our goal here is to do some kind of prediction, and we do the prediction by minimizing some model parameters. So our y, the y hat I being values in bigger y hat are simply the predicted values. So I want you to take note of these notations as we proceed. Yeah, so this is simply gets the best regression fit line by the best parameters value. So if we get a very good parameter values in our model that is for theta naught and then theta one, then it means that you have a very good algorithm or a very good linear function or model that accurately distinguish between the data point and give us a very good prediction. Yeah.
Yes,
I'll
that's
talk. I'll
correct.
talk about the cost function as we proceed. Yes,
Okay.
Benjamin, go ahead.
All right. Now I wanted to ask about the cost function.
Yes, I'll talk about the cost function later. Yes. So in linear regression, the cost function is simply an error function. So aim here is to minimize the observed data point and then the predicted data point. The observed data point simply refers to the actual data point and that in actual data point. And then the predicted data points are data points that were kind of predicted by the model itself or the linear function that we use to fit the data set. To minimize that distance as this distance is to use an interesting function known as the cost function. And this cost function, what it does is that it simply takes the difference between the predicted value and then the true values. And we normally also refer to this function in statistics as the mean square error function. And so the main idea about this function is to minimize the distance between the predicted values and then the observed value or the true values of the data point. And it comes in this equation that I have here, j of theta naught and theta one, which is equal to j being a function of theta naught and theta one, which is equal to 1 over 2, and where m simply refers to the number of samples that we have in the data set. And then your h naught, h theta of xi is simply the hypothesis function that we have in here. So this is simply the hypothesis function. And you subtract all this from your predicted value. So it's simply your actual value is simply the hypothesis function, which is the function that does the prediction minus the actual values of the data point. And we square this because we have want positive values, and we are dividing this function by 2 because of scaling reasons. Okay, so later on you realize that our aim is to minimize the model parameters or the cost function. And in minimizing the cost function, what we want to do is to differentiate. And you would agree with me that in mathematics, if you want to minimize anything, you just have to take the derivative of that particular. If you want to minimize the function, or minimize the function, the best thing or an equation, the best thing you can do is to take the derivative of that function. And that is a very good way of minimizing a particular function. So the 2 you see here is actually for a scaling reason. And then we want to square this because we simply want to have yes, I mean it's a distance, so that's basically what we want to do. So as I said earlier on, the the best way to um, get a very feasible linear function that distinguish clearly the data point is to come up with some values to give us a very good prediction. And the best way to achieve this is to best fit to achieve the best fit regression line. What we do is to our aim here is to simply predict the target values such that the error or the distance between the predicted value and the actual value minimizes. So that is the whole idea about the linear regression or the cost function. And we look at an interesting way of minimizing these model parameters as we go on. And not only the model parameters, there's also another parameters, a hyperparameter known as the learning rate, which simply determines the step size of the learning algorithm. So we look at that as we proceed. The learning rate is also very, very important and is simply a value that we choose to know to know how the function jumps, or the distance of the function, how well it moves towards the global minimum or the local minimum. So, and this brings us to what we call the gradient descent algorithm.
Sorry, Prince.
Yes. Any question? Yes.
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 Sorry to take you back. What's the M for in the cost function?
Sorry, could you speak
The
louder
M.
a bit? I think I can't hear you clearly.
Yeah. What's the M for? Would you kindly go back to the previous slide, which shows the cost function?
Yes, the
Yes,
cost
this
function.
M. Yes, there's this M in the cost function. What does it stand for?
You said what stands for? M.
Yes. What does
Yeah,
it
so I
denote?
said
Yes.
the M simply stands for the samples, the total number of samples that we have. So I said earlier on that we have M. So I said in a supervised learning process, and that is a subcategory of machine learning, the data sets used to train the model is simply called the training set. And this whole training set, from the first training set all the way to the last training set, so it's simply the number of samples that we have in the data set, or you can say the number of rows that we have. Okay, so it's samples, or the number of, we can also say the number of rows that we have. It simply defines the shape or the size of the data set that we have. I hope that's clear.
Yes, it is.
Yeah, so if you look at, if you are trying to do some form of analysis, the first thing you do is to check the shape or the size of the data set, and the M here simply refers to the total number of samples that we have. So the first sample all the way to the last sample, and this total number of samples is normally denoted as M. Uh, I hope that's clear. Can I proceed?
Yes, please.
Okay. So thanks very much. That was a very good question. If you have any other question, feel free to interrupt us.
Prince, just on the cost function, is this the general formula that we can use? I'm trying to relate between the cost function and the mean square error. I'm saying that, okay, for now, since this is a linear, because it's following linear functions, is this formula, is this the general formula, or maybe it's possible to stick to the one for mean square error, which explicitly states the difference between the observed and the predicted values?
Yeah, exactly. Thanks very much for pointing that out, Medicine. So as I said earlier on, the in linear regression, the cost function, or what we mostly also refers as the loss function, and the loss function. Let me stress on this thing again. There's actually a difference between the cost function and then the loss function. The loss function is simply your hypothesis function minus your true prediction or your true values. So this hypothesis function, which is your h theta of your xi minus your yi, is what we call the loss function. But the whole of this here is what we call the cost function.
Okay.
So
All right.
yeah, so what I'm saying is that this loss function, people also call it the mean square error in statistics. So it's simply the
Yes.
measure of how well the linear regression model fits the observed data. So what it does is that it simply quantifies the discrepancy between the predicted value of the model and then actual observed values. So I would say that the actual or the actual values can also be called the observed value. So what the cost function does is it's a in linear regression, it typically defines the average square difference between the predicted values and the actual value of the dependent variable in the observed data. And in statistics, this is normally represented mathematically. I think it will be 1 on n or 1 on m, multiplying the summation of the predicted value minus the actual value, and this is squared, right?
Yes. Yes.
Yes. So, and in our case, we want to also minimize the cost function, and in minimizing the cost function, we want to get parameter values. So we are going to differentiate the cost function with respect to the theta naught and the theta one, and we are doing that because we want a feasible value of theta one and theta naught that maximizes our chances of getting higher accuracy. So
Okay.
if you study this cost function, I think the only difference you can actually see here will be the two there. So apart from the two, it looks similar to what we call the
The mean
mean
square
square
error.
error
Yeah.
in
Yeah.
statistics. Yes. So the two is actually there for scaling reasons.
Okay.
So if you take the derivative of this, you realize that these two will come and multiply the whole function again. Is that right?
The two will
Yes.
cancel
So
with the other two. Okay.
exactly. So that these two just cancel these two, then it means that we are getting our mean square error back as we studied in statistics.
Ah,
So the
okay,
two is
okay, I
simply
see.
there for scaling reasons.
Ah, all right, thank you.
Yeah, okay.
I have a question. So
So thanks
we
for
are
pointing
saying
that
that
out.
you are saying
Yeah.
that we differentiate the function in order to minimize. So I know that the minimum usually happens when the derivative is zero. So does that mean that we equate to zero?
No, not actually. We will look at that as we proceed. So what we do is that in the gradient descent algorithm, we differentiate. Once we differentiate, we'll get a new model parameter. So when we get that new model parameter, we will subtract that new model parameter from the actual function that we have. Sorry, we take the think let me show this to you. What you are talking about, we will get there. It's simply this particular area where the new model parameter will be equal to this new model parameter minus the learning rate multiplying the hypothesis function or the cost function. So that's a very good point. Thanks for pointing that out, but we will get there. I will explain better when we get to this particular point. Okay. I hope that answers your question.
Yeah, it's still
Uh-huh.
a little
So
confusing, but I think we'll get to understand as we
yeah,
go on.
I don't know what you were trying to say actually. Could you rephrase what we were talking about?
Minimizing, I will sort of equate it to zero because the minimum and the maximum usually happens if you're talking about just a normal graph. We usually equate it to zero, and that when the derivative is 0, we say that will be the minimum point or either the maximum. So I was saying when we differentiate, if we are trying to minimize this error, when we differentiate, are we equating this to 0? That was my question. Because if we just differentiate the function without equating to 0, I don't see how that brings in the minimizing. That's what I was trying to find out.
Actually, when you differentiate, like in a mean square error, when you differentiate the derivative itself without equating it to 0, is the minimizer of whatever function you are using. So you don't need to equate it to 0. So it's the derivative itself which acts as a minimizer.
Exactly. So that's what I was trying to point out, that in mathematics, if you want to minimize a function or you might minimize an equation, what you do is simply to take the derivative of that particular equation or that particular equation. So let me say this: in linear regression, for you to minimize the cost function, we use an optimization algorithm, which is what I introduced to you right now, known as the gradient descent. And the gradient descent, what it simply does is that it goes through some kind of iterative process. And in this iterative process, it does two things. It updates the model parameters. So the model parameters that I just showed you, theta naught and theta 1, which represent the slope and the intercept. And it simply does this to find the values that minimizes the cost function and provide the best fit to the observed data. That is, you have a predicted value, but then it gradually goes through an optimization process, iterative process, until it finds the best fit for the actual data point that we have. I hope that helps. So it's simply an iterative process by adjusting the parameters, and it does this using the gradient descent algorithm. And the way to minimize this is simply by taking the derivative of the cost function. You don't have to equate this to 0. I hope that helps.
Yes, it does. Thank you so much.
Yeah, so now let's simply look at how these model parameters can be minimized using this idea of differentiating the model, the function with respect to the model parameters. Now let's focus on how to model this value. We have our cost function to be equal to what I have here, cost function to be equal to the whole of this. So our goal here is to minimize this cost function, and we have to take the derivative of this cost function. Now, so the first thing is to take the derivative with respect to theta 1 or theta naught. So please need to, this theta 1 here simply refers to theta naught in my illustration here. So that is just a bit of inconsistency, but I hope you can follow suit and simply get the concept of what I'm trying to say over here. So we take the derivative of the cost function with respect to theta 1. But I hope some of you have mathematics background and you'll be able to understand this. So taking derivative, so the second line, the derivative of the cost function, that is 1 on n of summation of the whole of the loss function. Remember I told you that y hat minus yi is the loss function. So you take the summation of this whole thing. And if you want to take the derivative of this, is simply, we just take 1 on n is simply a constant value. So you can just pull this constant value at 1 on n out. 1 on n out, and then you differentiate this value. So if you differentiate it, it will simply be your 2 multiplied by the loss function. And then remember, once you take the derivative of this, you'll be left with you differentiating the inside as well, which is the loss function. And that is what we have over here. So the next line, remember the y hat simply refers to the hypothesis function, which is your theta naught plus theta 1 xi. But then in this case, it's theta 1 plus theta 2 xi. So this is some kind of inconsistencies, but then I hope my writing part is here too. This is where I need this writing part. Okay, let me quickly connect my writing part and show you what these things means. But then I hope you guys can follow it. But so the next line 1 on n, then we are taking the derivative with respect to theta 2. So you realize that this theta 1, if you differentiate theta 1, it will be 0, and then take the derivative. Sorry, we are taking derivative with respect to theta 1. So it means that if you differentiate this one, you get 1. If you differentiate the whole of there's no theta 1, so this and this will go to 0. So in all, you are going to get this particular function multiply by 2. So this is an illustration where the denominator wasn't multiplied by 2. So if it were to be multiplied by 2, it means that you simply have 1 over n all the way to or multiplying the summation of y hat minus yi. And this is a way of minimizing the cost function by differentiating the cost function with respect to one of the modal parameter, which is theta 1. Yeah, do you have any question here so far? Or I should go over this step again?
No, this is fine.
Is it fine, or I should just go by it?
This is okay.
Okay.
We need to ask others.
All right, so let me try and then proceed. Having a minute to do this. Okay. Let's see.
Hi, Prince, are you there?
Yes, I'm here.
Okay.
I'm trying to illustrate this. So let me simply illustrate this right now for you to see how it looks like. All right, so as I said earlier on, we have the hypothesis function which is giving us um, giving us s equal to theta naught plus theta 1x, and then the cost function the cost function is simply equal to j of theta naught comma theta 1, theta 1, and this is equal to 1 over 2 sum of I all the way from 1 to n, and this is hypothesis function x I all squared. And what I'm saying is that our objective is to minimize the cost function. So what we do is that we simply take this cost function that we have and then use the idea of the gradient descent algorithm. So simply of j prime to just note that this is a way of theta naught comma theta 1. So the first thing we are doing here is to differentiate with respect to your theta naught, and this is equal to the derivative of theta naught pull 1 over 2m derivative of I is equal to all the way to m multiplied by a function minus your actual values squared. So if you are taking the derivative of this, then you have to simply pull this constant out, the constant 1 over 2m, and simply come out. So you get something like 1 over 2 all the way of m. Then you'll be left with, so you take the derivative of this. So if you take the derivative of that, you simply get 2 multiplying your hypothesis function I minus your true values. Then you'll be left with, that is the derivative. So you have to differentiate the function again. So you take the function, and remember this function, the hypothesis function that we have here. So this simply, the whole of this function, derivative of the hypothesis function is equal to theta naught of the hypothesis function, which is theta naught plus theta 1 x, the whole of this, minus your y.
I think you forgot the summation, sigma. The sum.
Yes, I think I missed the sum somewhere. The sum is supposed to come somewhere here.
Okay, just put it, yeah, next to the 1 over 2m. Yes.
So the summation is supposed to come somewhere here. So I equal to 1 all the way to n. So we can just have something like this. Then it's simple. So you simply get something like this. So 1 over 2m. Then your summation again, I all the way to 1 to m to 2. Then you have your hypothesis function of xi minus your yi. And then if you take the derivative of this one, you are going to get 1 minus, because this theta 1x doesn't depend on, and it doesn't have any theta not there. So the whole of this will be equal to 0 minus 0. So this is simple. So this is basically what you're going to get. So finally you'll be getting something like 1 over, sorry, 2 over 2m multiplied by your h theta over I x minus 1. So you simply get something like 1 over n h theta of x theta 1 of x minus 1. Yeah, so you get something like this after taking the derivative with respect to theta. I hope this is clear. So this is when you take the derivative with respect to theta naught. So you do the same thing for the other one by taking the derivative with respect to the gradient or the slope. So it's just the same idea again, the same strategy again. Then it's simply a way of minimizing the, the cost function just by minimizing the the model parameters. So you do the same thing for theta 1, 2 as well. You go through the same process again. Yeah, so the whole idea is in finding the coefficient of the linear equation, or that is the linear function that I introduced to you previously, and linear function that best fits the training data. Our objective here is to simply find a value of the model parameters that accurately minimizes the cost function. And the gradient descent is very interesting in the sense that that process of minimizing the cost function is moves in a negative direction of the cost function or the loss function. So that is what I actually illustrated here for you to see. Can you all see my screen? So that is the gradient descent, and then the minimum value that we are looking for is simply the local minimum. So the cost, as we tweak the weights, the cost, iteratively using this iterative process, the cost function simply minimizes. And I was saying that we need an incremental step, because if we have a learning rate that is extremely huge, the step function will just be jumping, and then we will never get to the local minimum. So we need a learning rate which is extremely small as possible to make sure that we get to the local minimum. And at the same time, we need the algorithm to be also very fast in getting to the local minimum. So we actually have to be strategic in choosing the learning rate. And in throughout the machine learning network, the feasible value that we use for the learning rate, which is our alpha, is 0.01. Other people also use 0.001 as well. And as I said earlier on, once you get once you do your we go through this optimization process, and we get learning algorithm. This theta 1 and theta naught are going to be chosen at random. There are sometimes chosen as weights in the neural network. It simply determines the strength of the network. So you get a new value, then you take this value and subtract the cost function multiplied by the learning rate, then you get a new value. Take the second one to once you go through the optimization process, you go through this differentiation process, and then you get a new value for your theta 2. Then you take this theta 2, and then you subtract the learning rate multiplied by your cost function from the new theta 2 that you have. Then you get your new theta 2. So it's now it's an iterative process, your cost function. Yes. So do you have any question up to this point? I think the next thing to do is to take you through how to actually build the algorithm from scratch. Then I'll be done for a day, hopefully. Then we continue hopefully on Friday. So do you have any question up to this point? So I should just proceed. Okay, so let me just
Cost function, right?
continue. Regression cost function.
So are there any other ones that we need to know?
Yeah, in logistic regression, there are other cost function. So
Oh,
once
okay.
we will get to logistic regression, which has a different cost function to this one. We actually have a lot of different cost functions. So let me quickly share the notebook with you. And I don't know if this thing can speed up. And please simply copy the link, paste it, and then you just have to. So we are using the same data set we've been using, or I just want to make sure that these things are consistent. Have you seen the link? Please, we don't have much time, so I would like
Where have you posted the link?
Yeah, I pasted it in the chat box.
No.
No, there is no link
We
there.
haven't received it.
There's no link.
Okay, a minute. I think you should have it now. Do you have it now?
Yes.
So you may just make a copy of the notebook, and then you can follow. So once you are all set, kindly let me know. Have you been successful in?
Yes, so far so good one.
Okay. Okay, so let me just proceed.
All right, Prince. Would you kindly provide the iris dataset in CSV format? What?
Yes, I made mention that we are still using the same arrays data set we've been using, so it hasn't changed actually. I think it's still the same array data set. The ones you have from the okay, let me just send it to you. So let me
In
quickly
CSV,
send you the iris
not in CSV format.
to your Google. Is it to your WhatsApp group or where? Because but because if I send you the link to download, I think that would also be much. Let me just try and see if I can send. Uh, to your platform. You mean you want to receive it on your WhatsApp platform?
Yes, but is it in CSV format?
All right, so I think you should receive it now. Um, Let me check. Yeah, so I think you should now. Can you all see my? All right. So if you are successful, then you should have something like this. Try and zoom in a bit. Like this, I think by now you know how to work. Like, then you just have to run the first or which are libraries in building the algorithm from. And then the next one is loading the data set. And I've taught you how to load data set from your Google Drive already. So there are missing values in the data set. So what we want to do is to proceed and then remove or drop all these missing values in the data set, which is simply what this line of code is doing. Because I'm going to use this data set to do our prediction. So we need to drop all missing values. It is not the time for us to take the mean of the mean of that particular column and then replace them with the missing values. It's kind of, you can simply drop them right away. And then the next line of code is to do some form of transformation. So here we want to transform the data set into so yeah, we are simply transforming this. So the data set and the other time, if you can recall, you realize that the arrays data set is in the form of a numpy array. So we simply have to take that data set and then transform it into a different shape. Print this. Data. So you take from the first data point, from the first one all the way to 500 points, and then we reshape this 500 data point that we have into 500 rows, but just want a single column. So that's simply what this data point is doing here. So you are taking all the data sets and then you're transforming. I mean, you are taking the the features, the number of features that you actually have, taking the number of features, and then you reshape this number of features that you have into 500 different rows and then one single column. Let me see. Yes, so the predicted is also giving valid. And we have the output values too as well. So it's simply a way of transforming the data set. So if you look at the actual data set, it's given in the form of numpy array. It is um, actually in the form of a data frame. So um, converting it into a NumPy array instead. So a NumPy array instead. So it's actually in the form of a data frame, kind of a data frame. So you convert, which is 700 rows and then 2 columns. Then okay, so 240, we pick the whole from the beginning all the way to 500 data points. So we're just taking a portion of it. You're not taking all the data points, just taking a portion of it. And then we reshape this into 500 different rows, but then we only need one particular column. So in a sense, this is simply a univariate way of doing a prediction with. So we are not doing the multivariate linear regression. We are simply doing the univariate linear regression. Yeah, so that is for the training. The first aspect that we did was for the training. So we took from the beginning the first 500 data points for the training, and then we left the rest. That is from 500 to 700, which is 200 data points. And this one will be reserved for testing. So exactly what we've done here, and we're also transforming this into 199 different rules, but then we need only one column. Okay, so now that we are done with the pre-processing and all that, working on the data set, let's just go into how to simply build this linear regression algorithm from scratch. Um, and you already know that this is simply a supervised learning algorithm. So guys, please give me like 2 minutes. I'll be back.
Hello? Hello?
Yeah, hello. He said we should give him 2
This is
minutes.
off, right? Okay.
Yeah.
Yeah, so sorry about that. I had to attend to something, so kind of. I hope you can hear me loud and clear. So quickly, let me go through the lines of code that I've written already. Okay, I have an emergency right now, so I think I'll close the session right here today, and then hopefully continue on Friday. Okay, hope that will be fine with you. I need to attend on something right now.
Okay, no problem, please.
All right,
Yeah.
Prince. Thank you so much.
Thank you so
Please
much.
keep the notebook. That's what I'll continue um,
All
on
right,
continue
thank you.
with on Friday. So please keep it.
All
And
right,
then
thank you.
remember that it means that on Friday we will be doing a lot to us. So thank you very much for joining today's session, and I will see you hopefully on Friday.
All right, thank you.
So I'll quickly share the slides I used today on the Google Classroom. If you don't have it, I'll the class reps to find a way to reach out to me, and I think I'll make it available to them. And then also, if you have any problems, feel free to also reach out to any of the mentors or myself.